Hi, today I want to talk to you about the moment generating function. We've considered this data of a discrete probability before, where x is a number of cats owned by a randomly chosen individual, so we'll use this probability distribution here. One thing that I'll note about a probability distribution um, is a valid density if two things hold. One is that the probability of x is greater than or equal to 0. And 2, so we see that's true. All the probabilities are 3/10, 4/10, 2/10, 1/10. Those are all greater than or equal to 0. And probability of like -1 or probability x equals 4, based on this table and this data, that probability is 0. Okay, so condition 1 is met. The second is that total probability is 1. Total probability is calculated by summing up the values from -infinity to infinity of p of x. And I'll rewrite that negative infinity because it's hard to see the negative. In this case, that just corresponds to adding up probability x is 0, 1, 2, and 3, and that gives us 10 out of 10, so that is also a check. Okay. Now that I've talked about a valid density, I want to talk to you about the moment generating function. The moment generating function is defined to be the expected value of e to the tx. That corresponds, using the properties of moment generating functions, to taking the sum from -infinity to infinity of e to the tx times by p of x. So let's calculate this. I'll list the probabilities first. The probability x is 0, that's 3/10 times by e to the tx. X is 0, so this gives us e to the 0. Plus, and one thing I'll note is e to the 0, that takes on the value of 1. The next is probability x equals 1, that's 4/10. So x is 1, this will be e to the t. Next is going to be the x being 2, p of x being 2 is 2/10. So that is going to be multiplied by e to the 2t. And finally, we can calculate the probability x is 3, which is 1/10, times by e to the x being 3 will be 3t. Okay, so that is the moment generating function. Hey, this is a function of t. One fundamental thing that we did in calculus is we differentiated. So why don't we just differentiate this? If I differentiate this, the derivative of 1 is 0, so I'll get 0 plus 4/10 times by 1 times by e to the t plus 2/10 times by 2 times by e to the 2t, and finally 1/10 times by 3 times by e to the 3t. Hey, if I were to add up all those things, but the e was not there, I'd get the expected value. That is, if I did this, I get 0 plus 4/10 plus another 4/10 plus 3/10, and that's equal to 1.1. That's equal to e of x. So here's a little fun fact. You could even call it a theorem if you wanted. The expected value of x, or the average, is just the derivative evaluated at 0. So that's going to be part 1. Part 2 is that if I want to take the expected value of x to the k, that's just going to mean take k derivatives, evaluate at 0. My apologies, that should be with respect to t, not x, and evaluate at t equals 0. Okay, so that's a fun fact. It's not too hard to prove. In fact, I'll prove 1. If I differentiate the definition of the expected value, I just have to take the derivative with respect to t of the summation from x equals minus infinity to infinity of e to the tx multiplied by p of x. Remember, this is a function of t, so x is just there along for the ride. I differentiate this exponential. Oh, and I should say evaluate at t equals 0, right? Well, we'll do that later. Okay, we'll differentiate e to the tx, that's the only term with a t in it. Derivative e to the tx is itself, but via the chain rule, I need to differentiate t times x. The derivative t times x, the one that's the variable is t, so I just get x multiplied by p of x. So if I plug in, and that should be the derivative because I differentiate. If I plug in t equals 0, I'll get 0 times by x multiplied by p of x, and that is the expected value of x, using that this term is in fact 1. Okay, thank you very much.